everybody. I hope everyone's having a wonderful day. So today we're going to be having some fun with logarithms. So before I talk about logarithms, I just want to get us up to speed a little bit about exponents. So I've talked about exponents before. I've also talked about logarithms before, but I'm going to go into a little bit more detail than I usually have been. So the first thing I'm going to do is I want to remind you what an exponent is. So there's this number raised to some power. This is often called the power or the exponent. So there's a couple of ways, and for dramatic purposes, I of course have to read it to you. A couple of ways that people often will read something like this b and the y here is someone would say b raised to the exponent or power of y. Or they might say b to the power of y. So if this is an integer, if y were an integer, a simple way of interpreting the exponent would be that I'm multiplying b y times. So a couple of conventions you should be aware of is that if I have a negative exponent, it means it's the reciprocal of that power. So for example, if I give you something like b to the minus 1, this is me just writing 1 over b to the 1. Or if I have b to the minus 2, this is just 1 over 2, sorry, not 2, it's 1 over what? It's b squared. And so on. Likewise, it should also be worth noting that if I gave you b to the 0, this is going to be equal to 1. So just be aware of that. So here are 4 properties that are pretty well known about exponents. The first one is, notice that if I have the base is the same between a product and there's exponents, I can add those exponents, such as here. If I have a quotient rule or quotient property of exponents, if I have a quotient like this, it just means I'm going to subtract the exponential terms like this. If I have a power, so if I have an exponent inside of parentheses like this, and this is raised to a power, say like n here, this just means that it's x to the product of m times n. And there's this power of a product. This means I can simply just split on products with the same exponent. I have examples of these things in the notes. I want to draw parallels to these guys over here, logarithms. So imagine I give you x, y, and b. These are all going to be positive integers. Sorry, not positive integers. What is that symbol? What is that symbol? It's a positive real number. And I'm going to assume that this b, which often is going to be referred to as the base, like I have over here, I'm going to assume if I ever say that it's for a valid base of the logarithm, I'm going to assume that it's a positive real number that isn't equal to 1. So some people might say, oh, some valid base of a logarithm. Or they might just say, just assume that you just aren't going to put a weird one in there like 1. That's going to be how I'm going to define the base. And I've deliberately used these symbols here, even though I use different ones right here, just to draw a connection between these two things. So this would be read as log base b of x, and it yields a value y. Now, the way we define the logarithm is actually as the inverse of exponentiation. So if I give you x is equal to b to the y, if I wanted to evaluate this, so for example, if this was 2 cubed or 2 raised to the power of 3, that would be 2 times 2 times 2, which is equal to 8. So x would be 8 here. Now I want to ask an inverted question to you. Instead of asking, okay, if I give you 8, and I know that exponent need to be such that b to the y is equal to x. So here I'm trying to determine the result of this calculation. Here I'm asking, if I give you the result of that calculation, what is the exponent that got me such that b to the y is equal to x? So it's just simply the inversion, or it's an inverse. So if I give you the result from over there, it should tell me what the exponent was, such that if I took b to the y, I would get x. So I went into more detail about this previously, but I just want to emphasize just a couple of things. So I've used some of these properties before, but I think it's important I state them. I may even give proofs for these in the future. So the first thing is the product rule. Notice that if I have a logarithmic term with a product, x and y here, that it simply gets distributed or gets split on that product into two separate sums like this. Now, you might ask, Dan, why does that make any sense? Well, I want you to really look at this picture. That picture, look at point 1 here, and then look at point 1 over here. Notice that over here, if I have the same base, x to the power of m and x to the power of n, notice that they have the same base. But what happens with the exponents? They add. So we're adding the exponent terms together. Remember, logarithm, I'm asking for what that exponent is. So it's no surprise that the result of a product like this would yield a sum on this right-hand side. Same idea with the quotient rule. So notice that 2 matches up with 2, 3 matches up with 3, but it looks a little strange at first when you see it. It's like, okay, well, that one over there had parentheses. Why would it be that this gets pulled down? The way I like to think about the power rule here, it makes things a little easier to remember, is imagine I take whatever's in the exponent here, whatever it is, I drop it out front, and then I end up with y times log base b of x. That's how I like to think about it. Makes it easy to remember. And likewise, if you don't like this y here, you can drag that back inside the logarithm, and you can place it right there as the exponent. So what we're going to do next is I'm going to prove the power rule of logarithm. So we're going to prove this property. So just as a reminder, so just if you're really out of the blue what logarithm is, so remember, if I give you log base 2 of 8, this would be equal to what? If I asked you 2 to the what is equal to 8, you would tell me it's 3 probably, right? So the result of this would be 3. Remember, I'm asking for what's the exponent that I have to raise this base to. So if I have 2 to the what, I get whatever is inside of x here. It's an inverse operation of exponentiation. I want to know what exponent I raise things to. Let's prove the power rule of logarithms. So just here's the statement of the theorem. So I'm going to let there be positive reals b, x, and y. And then I'm going to, of course, assume that b is not equal to 1, just because of my definition over there. I want you to actually think about what that would mean if I were to put b's equal to 1 in terms of that definition. I want you to think about the logarithm definition if it would make sense if b was equal to 1. But here's what we're going to prove. We're going to prove the power rule of logarithms, that log base b of x to the y is equal to y times log base b of x. So the whole idea is I want to drop that y out front, and now it becomes a product. So you might ask, Dan, what's the strategy when doing something like this? Well, all these properties over here, it really boils down to definitions. If you know the properties and the proofs for the exponentiation case, you just simply have to use definitions. So oftentimes the trick will be that I assign some variable that's going to be assigned to some value that's going to correspond to one of the sides. I'm going to try to make it equal to the other side. So very much this proof's going to be like, here's a definition. I'm going to use that definition to get to the next definition. So here we're going to start off with this. And this is a common strategy for dealing with these types of proofs. Because, like I said, there's a close relationship between exponentiation and logarithms. So I'm going to let z be equal to log base b of x. So I'm going to have this variable z. It's going to represent that, just log base b of x. So now I'm going to invoke the definition of a logarithm. So what did I tell you earlier about the definition of a logarithm? What does it mean? It means what? It means y is going to be equal to whatever is going to be that exponent that gets me to the result given that base. So what would it look like? It would look like b to the y is equal to x. So by the definition of a logarithm, So by the definition of a logarithm, what I want to do is I want to see what the heck is b to the z. So well, this, it would mean that b to the z is equal to what? It's equal to x, right? So you see how we're going to use our definitions to get things along? Then, here we go. Now watch this. We're going to use some properties of exponents here. Then, by raising both sides of the equation by exponent y, what would that mean? So I have x is equal to b to the z, right? So what I'm going to do is I'm going to raise each side of the equation by y. So I have b to the z, and this is going to be a y here. But what's this? This is b to the zy. Now you might ask, Dan, where did we go? How did we get to this step? Is this a valid thing to do? Now in the notes I go into more detail about how or why we can make this step. It's because of a very important property. It's about functions. So if I know, for example, that x is equal to y. So if I know if x is equal to y, one natural question is, okay, well, what can we do with that? If I know that this equality actually holds, and they're indeed on the same domain, you can imagine me raising both sides of this equation by an exponent, but that raising to an exponent is actually a function. If you really wanted to get nitty-gritty with this, what I'm saying is if x is equal to y, then if I defined a function on both their domains, so that they both can be used in part of that function, exponentiation is in fact one such thing, then it must be that f of x is equal to f of y. That's all I'm doing. So when I raise both sides to the exponent y, you got to imagine it like I've created another function, and since I know those two sides are equal, they must in fact be equal when I raise them by the same exponent. If you want more details about this, just check the notes. I have a little bit more detail about what a function is and what I mean by this. We've done this idea before, actually. I'm running out of breath. I'm really excited about this. We've done this idea before where we take the logarithm of both sides of an equality or an inequality. We've done this before. It's the same idea. So now I'm just going to proceed with this right here. So what does that mean? Log base b of x to the y is equal to what? What is it equal to? Because remember, x to the y is equal to b to the z times y. So if I place this inside of a logarithmic term like this, what should that mean? That should mean that log, well, let me put parentheses to make it a little clearer, log base b of b to the y times z, this equality must hold as well, right? Well, log base b of b to the y z is going to be equal to what? What is this equal to? I want you to think about it. Let's think. What does this look like? What does it look like, everybody? Well, look, what is this equal to? So one question I have is, what is this equal to? Well, think about it. I already gave you actually the answer. It's sitting right here, right? So log base b of b to the yz. So I've asked you, b to the what gets me b to the yz? Well, it's right here, right? It's y times z. And now here's where the fun comes in. Y times z, what is that equal to? Well, this is y times what? And what's z? It's x. Sorry, it's log base b of x, right? So what does that mean? So look at this. Log base. So we know this, right? And I've established that this is in fact equal to y log b of x. Are we done? Yes, we're done. Hence, log base b of x to the y is equal to y times log base b of x. And we're done. So this is a handy rule to know when you're evaluating logarithms. We're going to use this property in our next set of examples.